In this lesson, we'll be evaluating definite integrals. Evaluating a definite integral requires finding the antiderivative of a function. Let capital F of x be the antiderivative of lowercase f of x. So previously in calculus, we've learned the power rule, which was how we take the derivative of a polynomial function. So if capital F of x equals x to the n power, and we want lowercase f of x when we're finding the derivative, what we've learned is we would bring the exponent down, multiply it by whatever the coefficient is, times x to the n minus 1 power. So basically, again, we multiplied by the exponent, and then we also subtracted 1 from the previous exponent. So in this lesson, when we're talking about definite integrals, we have to essentially reverse this process. So I'm just going to call this reverse power rule for a non-technical term here. And think about, let's reverse all of those things. So if we were multiplying and subtracting when we took derivatives, we've got to be dividing and adding when we take an antiderivative. So if f of x, lowercase f of x, equals x to the n power, then capital F of x equals, well, we're going to add 1 to the exponent, and we are going to divide by that number. So it's x to the n plus 1 over n plus 1. For some functions, we can also use our knowledge of derivatives to help us determine the antiderivative. So for instance, if lowercase f of x is equal to cosine of x, the antiderivative of that is sine of x. If lowercase f of x equals e to the x, the antiderivative f of x equals e to the x. If we can determine a function's antiderivative, we can then evaluate a definite integral without a graph and without area formulas, as we've previously learned. At times, you might also see questions that give you an initial condition to help you find a value. All this basically leads to the second part of the Fundamental Theorem of Calculus. This deals with evaluating a definite integral. So if f of x is a continuous function on the closed interval a to b, and capital F of x is an antiderivative of lowercase f of x, then this is our way basically to find the value of a definite integral. We're going to take the antiderivative, plug in the bounds, and subtract. So the integral from a to b of f of x dx is equal to capital f of b minus capital F of a. So again, the process here is basically take the antiderivative. That's what that capital F of x represents. Then we would plug in the bounds. That's a and b. And then we would subtract the values that we get after plugging in the bounds. So it's always f of b minus f of a. All right, let's practice a whole bunch of questions using this idea. So for each, we're going to evaluate the definite integral, and we can also talk about how to check that answer in the calculator. Okay. At the end of this video, I'll add on a piece that shows how we could check that. All right, for number 1, we're evaluating the definite integral from 1 to 2 of x cubed dx. So using what I'm calling, again, the reverse power rule, I'd basically be adding 1 to the exponent, dividing by that number. We're going to evaluate that from 1 to 2. Okay. So this tells me that I'm going to plug 2 in. I'm going to plug 1 in, and I'm going to subtract those values. So this is going to give me 4 minus 1/4, or 0.25, and we are going to get 3.75 as our value of this definite integral. For number 2, evaluate the definite integral from -2 to 5 of 2x. With the coefficient of 2, you can copy it over, but you're going to see in a second that it's going to end up essentially canceling out with a new denominator, basically because that's equivalent to 1. So if I take the x and I do my reverse power rule, add 1 to the exponent, divide by that number, and again, we're going to evaluate that from -2 to 5, you can see that these 2's are going to go away here because that's just equivalent to multiplying by 1. So if you see this problem 2x and you are finding the antiderivative, if you just see that that's x squared, that's fine. You don't have to show the 2's canceling like I did here. So I'm really evaluating x squared from -2 to 5. So plug in 5, the upper bound. Plug in -2, your lower bound. And when I simplify this, I'm going to get 21 as my value. All right, for number 3, evaluate the definite integral from 0 to pi of 2 cosine x dx. All right, well, I'm going to copy down the 2. The antiderivative of cosine we said on the previous slide is sine, and we're going to evaluate this from 0 to pi. So I'm looking for 2 sine of pi minus 2 sine of 0. If you need to, you could use your sine curve, or I like to use the unit circle to help me figure out that value. So remember, here's 0, here's pi. And when I have the unit circle, sine is equal to the y-coordinate. So over at 0, the y-coordinate is 0. So this would be 2 times 0. Excuse me, so at pi here, let me plug in pi here, this would be 0, minus 2 times 0 here as well, and then I'm going to get 0 as my answer. So plugging in the upper bound first, I'm going to get the y-coordinate of 0, the lower bound 0 again, and so altogether that gives me 0. All right, for number 4, the definite integral from 2 to 4 of x cubed plus x squared minus x plus 1. So we have a big polynomial function here. So I'm going to do a reverse power rule, add 1 to the exponent, divide by the number. And I'm going to keep doing that for each term. If we think about 1 here and we're finding the antiderivative, this is basically the equivalent of x to the 0 power. Remember, anything to the 0 power is 1. So I'm just going to put this as 1x. If you wanted, you could put to the first power over 1, but you can see that that's basically redundant here. So what I'm going to do is I'm just going to simplify that and put x. And we're going to evaluate this whole expression from 2 to 4. All right, so let's plug 4 in for x. And then we're going to plug in 2. And we're going to simplify that whole thing. So for this, you can certainly use your calculator to help you add and subtract all of these fractions, or you can sit here and simplify it. If you want more time to simplify it, of course, you could pause this video, but this comes out to be 224 over 3. Okay, number 5. The integral from 0 to 1 of e to the x dx. So the antiderivative of e to the x is just itself, e to the x, and then we're going to be evaluating. So this is e to the first minus e to the 0. E to the first, or really anything to the first power, is just itself. E to the 0, or anything to the 0 power, is just 1, and we cannot combine that any further, so we're going to say that answer is e minus 1. All right, for number 6, integral from 1 to 4 of square root of x, and we could also think about this so that we have a rational exponent, that this is really x to the 1/2. So if I do my reverse power rule, when I add 1 to the exponent, I'm going to get 3 over 2. Then I have a choice here. Now I can divide by 3 over 2, but personally I don't like the way that looks. So what I'm going to do instead is I'm going to multiply by the reciprocal. We should remember that from algebra, dividing by a fraction or multiplying by the reciprocal will produce the same answer. So I'm going to use 2/3 x to the 3/2, and I'm going to evaluate that now using our bounds. All right, so I'm going to plug in 4. And then I'm going to plug in 1. And if we need to, we could rewrite this. If this is hard to compute, we could rewrite this back so that it's in radical format like the problem was. That might make it easier to come up with some answers here. So this is going to give me, let's see, 16 over 3 minus 2 over 3, or 14 over 3. All right, for the last two, these are going to be questions where there's an initial condition given to us. So initial condition is some coordinate that applies to the original function. So I know that f of -1 is equal to 7. Now, there are different ways you could go about these questions. I'm going to use this kind of set rule and formula, but we could also do some logical reasoning as well. So if I'm looking at this, I know that f prime of x is equals to 6x, and I'm going to use the initial condition and that information to evaluate f of 0. So I like to think about the rule as initial condition plus our integral. So we need to find the antiderivative of f prime of x. And then let's talk about our bounds here. So the way that I'm going to label this is the lower bound is what I consider what we know, an x value we know something about. The upper bound is what we want to know. So let's try and kind of substitute in here. The initial condition is 7. We know that that happens at -1. We want to know what happens at 0, and then of f prime of x dx. So now let's evaluate this. So this is 7 plus the integral from -1 to 0 of 6x dx, right? Because we were given the derivative in the original question. So now I'm going to integrate over here. So this is going to give me 6x squared over 2. Or we could simplify that to 7 plus 3x squared. And we're going to now evaluate that expression using our bounds. So that's 7 plus 3 times 0 squared minus 7 plus 3 times -1 squared. And when I simplify all of that here, I'm going to get 4 as my value of f of 0. All right, let's try one more like that. So if we look at number 8, f prime of x is equal to 3x squared minus 5. F of 1 equals -2, and we're going to find f of 3. So let's use our rule, initial condition plus the integral. The initial condition is the y value, so we know -2. The lower bound here is going to be 1 because basically these two pieces need to correspond to that given fact, that initial condition. So we know f of 1 equals -2. The upper bound is what we want to know, so we want to know what happens at 3. And our function here is 3x squared minus 5, and then dx. All right, if we integrate that, we are going to get 3x cubed over 3, which is really x cubed, minus 5x, and we're going to evaluate that using our bounds. So I'm going to be plugging in 3, then I'm going to be plugging in 1, and when I simplify this whole entire expression here, I'm going to get 14. Hopefully this lesson helps you understand a little bit more about the fundamental theorem of calculus and how to evaluate definite integrals. So I mentioned that at the end of the video, I'd be showing how you can evaluate a definite integral using your calculator. So I'm just going to use number 1 from the video and show you how to evaluate on a TI-84. So this question was the definite integral from 1 to 2 of x cubed dx. In order to check our answer in the calculator, we're going to be hitting the math button. And then you can either arrow down to choice 9 or just press 9. And you'll see that you'll get a nice definite integral setup. So I'm going to just simply type in the numbers from our question, which means 1 is our lower bound. Use my arrow keys to get to the upper bound where I'm going to type in 2. And then use my arrow keys again, and I'm going to type in our function, which was x cubed. Once I see that everything here matches our question in number 1, I just press the enter key. And you can see that I can confirm my answer from before was correct, that that integral is equal to 3.75.